Hi, my name is Tim Woodford, and today I'll be presenting our paper SpaceBeam, LiDAR-Driven One-Shot mmWave Beam Management. Emerging wireless network applications such as wireless VR, vehicle-to-everything communications, and cloud-controlled robotics all require both high throughput and low latency simultaneously. Modern wireless networking technologies have made great strides in increasing throughput or reducing latency individually, but no technology can currently provide both. For conventional sub-6 GHz networks, we generally require time division multiplexing due to limited spectrum and limited opportunities for spatial multiplexing in this spectrum. To achieve ultra-low latency, the 5G NR standard proposes ultra-reliable low-latency communications, or URLLC, which preempt ordinary communications to deliver certain high-priority messages. However, this mechanism is only designed to provide much more limited throughput for a small subset of the messages in the network. So it's not suitable for the sorts of applications that we are interested in here. Millimeter wavelength networking technologies such as 802.11ay use fine-grained spatial multiplexing so that we can send many data streams simultaneously, rather than having to use time division multiplexing. However, the high directionality of millimeter wave networks leads to a different type of overhead, the overhead required to select beams. Currently, networks require exhaustive measurements of the millimeter wavelength channel to select their directional beams. This means that we must scan all possible beams. This scanning process must be repeated every time one or more nodes moves in the network. The amount of time required to complete this beam training process increases at least linearly with the number of users in the network. This beam training must be completed while all other traffic in the network is paused. So this actually reduces the benefit that we get from spatial multiplexing. SpaceBeam achieves low latency millimeter wavelength wireless networking by eliminating this beam scanning period. This removes the source of periodic high latency. Obviously, the question is how we can replace this training period. To do this, we will first discuss the characteristics of the millimeter wave channel, to understand why this beam training is necessary and how we might replace it. So the problem in general is that the millimeter wavelength channel is sparse. So this has a few different implications. So the first here is that only a few directional beams will actually have usable SNR. And the second issue there is that whenever our device moves, the existing beams that we're using are often likely to no longer be usable. So the connection will become unstable unless we go back and update our beams. The second implication is that a single measurement of the millimeter wave channel gives us very little information about what the millimeter wave channel will look like at another nearby location. Our first key insight into solving this overhead problem is that if we could build a complete dense model of the wireless channel environment, then we would be able to select the optimal set of beams for any given set of radio locations. For example, if the node in this picture moved, then we would be able to use our existing channel environment model for beam selection without any need for exhaustive scanning. However, this raises a rather obvious problem. How would we build such a map? Remember that any measurements that we take using millimeter wavelength devices, including our radios, or even if we were to use radars, the results would be sparse. So to build a complete dense model of an indoor room, for example, we need to sample all possible locations in the room where a radio could be. Since millimeter wave radios can move freely in 3D space for applications such as wireless VR, such sampling could take a rather enormous amount of time and would rapidly become infeasible in many environments. Our solution is to use an infrared LiDAR camera to map the environment. Infrared radiation backscatters from most surfaces, meaning that it can quickly build a dense 3D model. However, infrared behaves very differently from millimeter wave RF, so we must devise solutions to bridge the gap between the infrared representation of the scene and the representation of the scene used by millimeter wave radios. The core contributions of SpaceBeam are the methods that we use to bridge this gap between the millimeter wave communications environment and the infrared-based LiDAR map. The first gap that we address between infrared and millimeter wave is the reflection properties of different objects in the environment. So for example, in this scene, we can see that there's a couch on the right. So that would be a rather bad reflector. we basically can't use that at all for communications. Directly ahead of us, we see that there's drywall, so that will cause a loss of maybe 10 decibels. So in some cases, it would still be usable as a reflector that we might want to use, depending on other factors in the environment. And then finally, there are very good reflectors, often metal or glass, and those cause very, very little loss. So if we want to use our infrared model to somehow select the beams that we're using for communications, we need some way to differentiate between the reflection properties of all these different objects in the environment. The second gap that we face between infrared-based LiDAR models and the millimeter wave channel is that the infrared models are noisy. So even if we use a state-of-the-art LiDAR, we use a very good denoising model, pretty much no matter what we do, we're still going to end up with some sort of noise in the 3D model. And that will significantly interfere with our RF ray tracing process. So the second thing that we need to do is somehow make our ray tracing process robust to the sorts of noise that we see in these LiDAR models. So the first problem that we want to look at is figuring out which objects in the environment will make good reflectors. So in general, with millimeter wave reflections, there are two different ways that we lose power when the signal reflects off of an object. So the first is dielectric or transmission-related loss. So basically, part of the power is transmitted through the surface and just keeps going. The other factor is diffuse scattering, which is generally due to roughness in the surface. And that's what we'll look at right now. So the advantage of looking at this sort of scattering is that there's a single material dependent property that we can measure. And then once we know that delta H value, we can actually find the rough surface scattering at any frequency. And again, this loss is in addition to the dielectric reflection loss, but we're not going to look too deep into that right now. So to determine the effects of diffuse scattering on the millimeter wave reflection strength, we need to find the value of delta H using only infrared data. So to do this, first we realize that the rough surface loss is negligible when the incidence angle is 0, which means that the camera sees a specular reflection from its built-in IR emitter. Second, we realize that at any other angle, we're only going to receive backscatter, which is proportional to the roughness of the surface. We can actually see both the specular reflection and backscatter in a single IR image from our camera. Therefore, we can estimate delta H using only a single IR intensity image, with a range of incident angles coming from the same surface. We measure the reflection loss and LiDAR forward and backscatter of multiple objects, and find that the surface roughness we measure using IR is strongly correlated with millimeter wave reflection loss. This suggests that we can use surface roughness as measured with IR to rank ambient reflectors by reflection loss, and we can do this even without knowledge of the object's dielectric properties. Finally, we evaluate the effect of this sort of reflection loss estimation on how well we can select the optimal beam in any given environment. So we consider three different methods. So the loss oracle method represents an ideal material estimation. Material ID represents the method that I just described, and the path loss case doesn't try to estimate the reflection loss at all. We find that the method that I just described actually improves the worst case SNR performance by 6 decibels, improves the average SNR performance by over 1 decibel, and we also find that the gap between the performance that we achieve and the ideal performance case is relatively small. Next, we'll discuss ray tracing. So ray tracing converts the dense 3D model that we just built back to the sparse set of millimeter wave paths that we need to use to select beams with good SNR. The problem we face is that existing ray tracing solutions are designed for cases like the one on the right, as a relatively small number of mostly flat surfaces. This is the sort of model that we can build easily in CAD software, and it works well because a human can easily determine which parts of the environment are most important to include in the model. The model on the left is the sort of model that we actually get from the LiDAR measurements. There are reconstruction artifacts, there's noise, there's a very dense set of planes with slightly incorrect normal values. So why is noise such a problem when we are conducting RF ray tracing? Let's consider a case with two radios where we want to find a reflecting point on an adjacent wall that we can use to communicate. On the left, we have a CAD model. We can use some simple geometric methods to find the reflecting point. On the right, we consider a LiDAR-based model, and specifically we have a reconstruction error near the reflection point. Because the normal vector associated with that plane where we want to find the reflection is not quite correct, we actually can't find a location in the LiDAR model where there would be a specular reflection between these two radios. To solve this problem, we introduce an error tolerance into the reflection angle in our LiDAR model. This generates a large number of additional paths, so we use a clustering algorithm to estimate where the true reflection location is located. The second problem that we face is that reconstruction artifacts, such as the one on the right, may introduce additional false paths that would not actually exist in the real millimeter wave channel. For example, in a real environment that we measured, the ray tracing algorithm discovers reflection points on small surfaces on the window frame. By analyzing the size and shape of these clusters, we can eliminate these false paths while only eliminating a very small number of good paths. Finally, we compare our results to some alternatives. An obvious alternative to our method would be to reconstruct the entire environment as a small subset of planes to automatically create a CAD-like model, but our method significantly outperforms this automated plane fitting model. In particular, we find that the conventional wireless in-sight ray tracer misses the majority of available millimeter wave paths, while the plane fitting method struggles in geometrically complex environments such as a garage. The final gap that we must bridge is the time between the sensor data collection and the actual real-time beam selection. To make SpaceBeam work on even low-profile devices, we measured the environment in advance. We then pre-calculate a lookup table which maps the current location of each device to a set of available beams. We send this lookup table to each device. To handle environment dynamics, such as moving blockages, we include a heuristic which detects drops in SNR and then rapidly switches to an alternate beam. Now we evaluate how well we can handle changes in the environment without rerunning our LiDAR measurement. Instead, we handle dynamics using only the fast failover mechanism. In scenario 1, we introduce a single moving blockage into the room, such as a person. In scenario 2, we move many small objects in the room. In scenario 3, we completely move a large metal reflector. Scenarios 1 and 2 offer near optimal performance as compared with the Oracle or Perfect Knowledge case. It isn't until we move a large reflector that we actually see a significant performance reduction and we would need to rerun the LiDAR measurement. Finally, we conduct a set of system-level evaluations in 3 different indoor environments: one empty room, one room with furnishings, and one indoor garage. We compare the throughput of our system to the default multi-user support in 802.11ad. We also compare it to many-to-many beam alignment, which is a state-of-the-art extension to 802.11ad, which offers improved spatial multiplexing. While this extension to 802.11ad can match SpaceBeam with lower numbers of users, the benefits of SpaceBeam's lower overhead become clear as more users join the network. We have almost 2 times improvement in the 12 to 14 user range. SpaceBeam also has significantly lower average latency than these alternatives, again because it eliminates this beam measurement overhead. To summarize, we developed 3 major contributions. Material detection selects the best reflectors without requiring any additional millimeter wave measurements. Ray tracing operates on noisy LiDAR-generated 3D models. And finally, we have a fast failover method, which allows us to handle environment dynamics without requiring additional LiDAR updates. In the end, our method provides a 95% lower channel measurement overhead, 80% lower average latency, and twice the average throughput of existing methods. Our work demonstrates new principles for using cross-domain sensing to improve millimeter wave performance. With minor modifications, our work can be extended to outdoor vehicle-to-everything scenarios, and it also has potential for other applications, such as coverage modeling. See our paper for more details about SpaceBeam's algorithms and performance benefits in the MobiSys 2021 conference.